like alkenes, we can hydrogenate alkynes, meaning we add hydrogen gas across the pi bond. So if I take this, this is an internal alkyne, and add H2 across that pi bond, it will add syn. So let's make a note here that it is syn addition. And we'll go from the triple bond to the double bond. And this has 1, 2, 3, 4, 5, 6 carbons. So I'm going to just draw a 6 carbon chain. This last carbon I'm going to put down so that when I have my double bond here, I can draw my 2 hydrogens syn. Again, if you want to number it to keep track, let's number it from the right so it's more IUPAC style. We have this, and the pi bond is still between 2 and 3. This reaction is known as a reduction, and we often abbreviate reductions with the H symbol in brackets. And when you have a reduction, that means, in a simple sense, you're increasing the number of CH bonds or decreasing the number of CO bonds. So in this case, it's just increasing the number of CH bonds. The problem is you actually can't stop at this stage. So just to give you an idea of how this reaction is set up, usually, you'll take your alkyne, have it in some solvent, add the palladium catalyst, and then the hydrogen is a gas. So what we often do is put a balloon filled with hydrogen above the reaction flask or on the reaction flask. And what that does is it keeps an atmosphere of hydrogen in the flask. Well, it's very hard to control 1 mole of gas to 1 mole of alkyne. So what will happen is this hydrogen, because it's in excess, it's going to continue to react and will further reduce the alkene. So this will continue and will reduce the alkene to the alkane. Here's our 6 carbons. And if you want to draw the hydrogens in, you can, or you can just leave it like this. So in carbon 2, we end up with 2 hydrogens added new, 3, 2 hydrogens added new. So unlike adding HCl or Cl2 to an alkyne where you can stop after one equivalent and stop at the alkene, with the hydrogenation, you cannot stop here. It goes all the way to the alkane. But now thinking synthetically, it might be beneficial if there were a way to stop at this alkene. So perhaps we could start with an alkyne, reduce it to an alkene, and then take that alkene onto something else through a reaction. So there's a way to do this. What we can do is poison the catalyst, making it unreactive to the alkene. By poisoning it, it's only going to react with the alkyne, and then once you get to the alkene, it's unreactive towards it. What the poison is that we use is called Lynn-Lars catalyst. And what Lynn-Lars catalyst is a special combination of palladium, calcium carbonate, lead acetate, and quinoline. Most organic chemists don't even want to remember all of this, so we just write Lynn-Lars catalyst over the arrow. So if you see that, just think syn addition of H2, and you stop at the cis alkene. So again, I think it's often useful to number this. Let's draw a 6-carbon chain. But one thing you want to be careful of is making sure that 2 and 3 ends up becoming a cis double bond. So sometimes it's easier to actually draw your double bond first. There's 2 and 3. And then draw carbon 1 attached to that. And then draw carbon 4 cis. And then you can just add in 5 and 6. Now that we have our cis alkene, we're done. Now you can draw in the hydrogens if you want, or leave them implied. So I'll draw them here in gray so you can see them, but you don't have to draw those hydrogen in.